Good afternoon, everybody. I hope you had a relaxing and enjoyable Thanksgiving holiday. On behalf of the Texas A&M Energy Institute, it is my great pleasure to welcome you to our annual Distinguished Lecture in Energy, which is going to be virtual this year. We are all experiencing unprecedented challenges with the pandemic and the societal and economic impact that it has caused. The disruptions in the supply chains and our everyday life, the remote work almost completely changing our habits and functions. The energy sector has also been greatly affected, with falling demands, even negative at some point oil prices. These factors, combined with emerging business and societal drivers towards sustainability, decarbonization, electrification, digitization, and in general, managing the energy transition landscape, have been providing unique challenges for the energy value and supply chain of the future as it is being redefined and reshaped. Our distinguished speaker today, Mr. Ryan Sitton, is very well positioned to navigate us through some of these challenges, having a successful career that spans the public service and the business world. Ryan is the founder of Pinnacle, with 20 years of experience in creating data management systems for equipment integrity and reliability, working closely with some of the world's largest companies in the water, oil and gas, and mining industries. He's considered a leading expert in energy market analytics. He has served as Texas Railroad Commissioner, the chief energy regulator for the state of Texas from 2014 until very recently. He is a vivid entrepreneur, having founded multiple companies, including software development, commercial real estate development, and leadership training companies. Ryan earned his Bachelor of Science in Mechanical Engineering from Texas A&M University. He is a very proud Aggie, and he is also chairing our Energy Institute's External Advisory Board. Please join me in very warmly welcoming Ryan Sitton to deliver the Texas A&M Energy Institute 2020 Distinguished Lecture in Energy, entitled Quantitative Decisions, Combining Experts and Data to Improve Complex Systems. Ryan, the virtual floor is yours.
Thank you, Stratus. It is good to be with you, and it's good to be with everyone here virtually. You know, it has been, as Stratus said, a long period of a new normal, right? I miss seeing the faces in the room as we talk about interesting topics, such as quantitative decisions, energy markets, talk about data analytics and complex analyses, quantitative systems. The thing is, we're not doing that. And so I have one request for you. I'm going to lecture, since it's a distinguished lecture series, for 30 minutes, give or take. And at the end of that, I would like you to ask me questions. It's a little less comfortable when we're not in the room and looking eye to eye, but do it anyway. Imagine that while we are having this discussion, it's just you and me. And I'm going to share some bold ideas with you today, the kind of ideas that we don't get lectured to us in a classroom, or we may not hear in a standard textbook of generally accepted practice. These are things that are more forward-looking, the ideas that may shape some of the future of our world and our society. And I like those bold ideas to end in discussion. But let's start with an imagination exercise. Imagine that you were the equivalent of John D. Rockefeller, but instead of starting Standard Oil in 1870, you were running most of the U.S. oil industry in 1970. Now, in 1970, the U.S. oil industry was on a massive boom. And coming into the 1970s, we were about to hit some really interesting market fluctuations driven by the Middle East oil embargoes. Now, we'll come back to that in just a second, but imagine what it would have been like to be running the U.S. oil industry at the time of the Middle East oil embargoes. Now, another situation, imagine what it must be like to be the president of the United States in the middle of COVID-19 and dealing with all of the societal and political ramifications of the world's largest modern pandemic. Another situation, imagine what it would be like to be the general manager of a struggling Major League Baseball team. And you may say, what do the three of these things have in common? Running the U.S. oil industry at the time of the Middle East oil embargoes, serving as president of the United States in the middle of the worst global pandemic, arguably in history, or running a struggling Major League Baseball team. What would the three of these things have in common that would have us talking today? They are all examples of complex systems in which making the decisions were very difficult for people who have been in those roles, and which we can look at and learn some interesting lessons. Well, let's approach them in history. Let's start with our John D. Rockefeller 100 years after Standard Oil was started, and talk about what was going on in the oil industry and what lessons we can steal by watching what happened through the history of the oil business. We've talked about imagining the situation, but first let's talk about what has happened with oil prices over the last 70 years. This graph is adjusted for inflation, and you don't have to get into the specifics of the prices, but you'll notice there are two spikes in oil prices between 1950 and 2020. One occurred right at the end of the 1970s, early 1980s, and one occurred in 2008, 2009 timeframe. Both of these spikes were driven by fear of oil shortages, and both spikes resulted in some dramatic changes to the world of energy as we know it. Now, what was the reaction to these spikes in oil prices? Well, we'll look at another graph. This is a graph of oil rigs in operation. You'll notice there's a big spike in the early 1980s, and not quite as big a spike, but a fairly sustained spike that occurred right after 2010. In other words, the spike in high oil prices resulted in a ramp up in drilling activity. Now, if we were to go back to the 1970s and walk through what happened in the Middle East oil embargo, let's set the stage. You'll remember that the United States was getting involved, if you will, and working with the newly formed Israeli government that had just come into being after World War II. And in the Middle East, there was a lot of tension over the establishment of the new Israeli government, New Israel, and the taking of the land to use for that new population, that new country. And in the 1970s, there was a series of conflicts in which the United States weighed in on behalf of Israel. And in response, the brand newly formed OPEC led the Middle East countries to boycott sending of oil to the United States. Now, at the time, Middle East oil only represented a few percentage, 10% of U.S. oil imports, but it was a big enough number that it caused rampant fear. I was born in 1975, so I don't remember it personally, but my parents sure do. My parents, who had to wait in line for gas and could only buy gasoline on certain days because the government was having to ration oil in response to the shortage caused by the Middle East oil embargo. Go back to our price graph. You'll notice that adjusted for inflation, oil prices were down in the right around $20 a barrel range at the beginning of the 1970s. Before that decade would let out, oil prices got over $120 a barrel, multiplied by 6 as the world was terrified, as the United States was scared of shortage of oil, and we began to drill, baby, drill. We ramped up drilling rigs to 4,500 running in the United States at the time, trying to put more oil on the market to fill this demand. Now, if you were the head of the U.S. oil industry at this point in history you felt pretty good. Man, we are dominating. Oil prices are high. We're producing more oil than we ever have. However, you had been set up to fail. By the time we got to the beginning of the 1980s, 1982, 1983, the Middle East oil embargoes were lifted, and two other things happened. The Cold War had reached a fever pitch with the Soviet Union, and a newly elected Ronald Reagan was looking for mechanisms to cripple the Soviet Union's economic prowess. And Russia has been a net oil exporter for decades. So Ronald Reagan, working with the Saudi prince, the Saudi government leadership, decided that it was in the national interest, geopolitical stability interests, to flood the market with oil. So at the end of the 1970s, beginning of 1980s, U.S. oil production was at an all-time high. The Middle East oil embargo gets lifted, and Saudi Arabia pushes excess oil on the market. What happens? Oil prices crash almost all the way back down to where they were at the beginning of 1970. But this time, billions of dollars have been invested in new refining infrastructure, new drilling infrastructure, and new oil production. As a result, in the 1980s, Houston area, which is heavily, and at the time even more heavily dependent on the oil business, saw nearly half of the homes purchased in the first half of the 1980s end in bankruptcy before the last half of the 1980s. It was the worst economic recession experienced in Houston even today because of the dependency on U.S. oil. Now, this economic downturn would not be limited to just the U.S. oil industry. You see, if you look around the world in, say, manufacturing, and you say, what are the key drivers of the economics of manufacturing? They are labor costs, raw material costs, and in many cases, energy costs. As the United States went into a sustained period of destabilized energy, as our oil industries were faltering and we were buying more and more energy overseas, it was wreaking havoc on U.S. manufacturing. And from the mid-1980s all the way up into the early 2000s, for nearly a 25-year period, you saw manufacturing move in large scale overseas. At the same time, U.S. went from a point of importing almost zero of the energy that we used, or even being a net energy exporter, to by 2005, 2006, importing nearly 30% of the energy that we used in this country. So the ramifications of this massive spike in oil prices, and then a gigantic change in oil markets right afterwards, driven off of a large-scale ramp-up in energy production, would wreak havoc on U.S. manufacturing and the U.S. economy for decades to come. But all of this began to change in 2005. If you look back at the global energy markets and you say, well, what happened that changed the landscape in 2005, you would see that energy prices began to spike again. And all of a sudden, as energy prices were coming up, U.S. entrepreneurs, U.S. industry were getting back into business. New ability to produce oil in the Permian Basin using a combination of horizontal drilling and multi-stage hydraulic fracturing opened up resources we never thought were economically developable before. And by the time we get to today, in fact, 2019, the United States was importing less than 30% of its oil. And once again, we were a net energy exporter. So we see these massive shifts going on in the landscape around us. Yet at the time when these things were shifting, why couldn't we predict this? What was happening that we couldn't see the landscape coming, model out these complex decisions? In fact, if you were, again, the John D. Rockefeller of the 1970s, and you were responsible for the U.S. oil industry, could you today look back and make different decisions about what you might have done then? And maybe even be making different decisions today. Let's jump forward to what's happening as we speak. Right now, the U.S. refining industry is the #1 refining. We refine more oil in the United States than any country by a healthy margin. The United States refines between 18 and 19 million barrels a day of crude oil. Second to us is China, which today refines about 14 million barrels a day of crude oil. However, that gap is shrinking, and it's shrinking fast. In the last year, just because of coronavirus and market downturns, the United States has shut down, right, I think to count today is 6 refineries, with another half a dozen dramatically reducing their capacity. The United States at its low point in May and June, we were only processing about 13 million barrels a day of crude oil. It's come up since then, but still our actual throughput is really reduced. In the meantime, China is bringing new refineries online every day. And as we look at the landscape going forward, U.S. oil production is dropping. Our natural gas prices are coming up. And our ability to harness the oil and gas industry here at home is under fairly serious threat. In the meantime, China's oil and gas industry is growing and thriving. Interestingly enough, one of the challenges that we're facing is not just the coronavirus, not just the market challenges and the reduced demand for gasoline because people are doing what we're doing right now. We're also seeing influence, we're seeing pressure from environmental groups, we're seeing pressure from politicians to convert, to subsidize alternative energy sources to drive demand down even further. Well, if we look out, what can we see coming that these guys didn't see in the 1970s and 80s? And that's the question that we'll answer here in a minute. But let's shift gears and talk about another market reality that is independent of what's happening in oil today. And this is the reality of Major League Baseball. In 1977, at the same time as the second Middle East oil embargo was going on, a guy named Bill James was writing a book. Now, Bill James, if you've never heard his name before, was the foundation. He was kind of the godfather of the modern day statistical analysis methods in Major League Baseball. Most people haven't heard his name because if you've seen movies like Moneyball or if you've read the book Astro Ball, you're hearing about more of the modern heroes. The Billy Beane, who was the general manager of the Oakland Athletics, that put some of the statistics to use for the first time in history. But all the way back in 1977, Bill James was looking at the world of Major League Baseball with a scrutinous eye. Bill James said, you know, I'm watching this sport suck in more data than any other sport in history. This is in the 1970s. And as people were looking at things like batting average and on-base percentage, Billy Beane was saying, you know, there is a different combination of statistics that actually correlates to wins more effectively. But in 1977, no one cared. Through the 1980s, no one cared. Through the 1990s, no one cared. Over 2 decades later, Billy Beane is managing the Oakland Athletics, and Beane's got a problem. And if you've seen the movie Moneyball, you know how this story goes. Billy Beane had been fortunate to draft some players to the Oakland Athletics who turned out to be future all-stars. But because they didn't know that when he drafted them, he could afford to pay them the relatively middle-range salaries that they commanded. But after 2, 3, 4 years of the Oakland Athletics, they became free market baseball players and went on, 1 or 2 of them, to the New York Yankees, literally multiplying their pay by, an order of magnitude. Now Billy Beane was stuck with a new quandary. I've got to go out and recruit players that I can afford to pay on a very small budget salary compared to big time programs like the New York Yankees and still try to be competitive. Beane knew that he couldn't do this using the same methods that the programs like the Boston Red Sox and New York Yankees, the 2 highest payrolls in baseball, could afford. So he went out about doing it differently. He said, what data is out there? And as the story goes, Beane started looking at some of the stuff written by Bill James and written by other people at the time and ended up finding a scout, an economics major who had worked for another ball club, recruited him to come to the Oakland Athletics, and together they put together a set of statistics. And if you watch the movie Moneyball, there's a famous scene that is a fairly, according to the people who were the real life participants, that the scene is fairly accurate. Here Billy Beane is sitting in a room full of baseball scout experts. And he's telling these experts, we've got to recruit differently. And the experts, who have a combined 200 years of baseball scouting experience, are telling him, Billy, you're an idiot. We've been doing this for decades. We know how to find good baseball players. Trust us. And Beane says, I can't trust you because the game is changing faster than you are. And he says, we don't care about the good old statistics you've always used. What we care about, and he points at the young economics major, and the kid says, whether they get on base. And so Beane begins to shift the way they use data and look at new data analytics. And as a result, that next year, the Oakland Athletics would set the record for the longest winning streak in American League history, using a bunch of players that nobody else thought were valuable. Now, this is, again, an example of insight into something where you look at a set of data and see something nobody else can see, Just like we're looking back saying, why didn't these guys see the dramatic downturn coming in the oil business if there was one fact that if there were facts that they were missing while other people saw it? Well, now let's take on something that's right now, that's happening in the world around us right now. What about coronavirus? Right now, we hear every day updates in terms of the number of people, number of cases that have been reported. We even hear numbers about the number of people who have died. And the question we are asking ourselves is, as we are now literally today, some cities are announcing a new round of lockdowns, or they're trying to evaluate whether to put further restrictions in place. How much good does it do? If we were to go back into March and April and May of this year, would we make the same decisions that people made at that time? Now, at the time, we didn't have good data, or the data we had was very new. But as months went on and the CDC was reporting, is number of cases, which is what we hear about most in the media, is that the best indicator of the positive impacts or negative impacts of moves? We were talking with a data science group in Tennessee just 2 weeks ago. And the theory amongst that group was no, actually. Well, what about number of deaths? If it's not number of cases, maybe it's number of fatalities? No, the group thought, that's not it either. Well, what would it be? And one of the men spoke up and he said, if we really were trying to understand the overall societal impacts of coronavirus, we would look at a statistic called excess fatalities. What is excess fatalities? Well, if you look at the average number of fatalities per year, and you look at, in the United States, on a per person basis or per capita basis, you would say, how many fatalities have we had in this country over and above the ones we would normally have? I said, okay, well, I assume they're higher this year. And he said, that's right, Ryan, they are higher this year. However, they're not caused by what you'd think they'd be caused by. Okay, well, today we're reporting 260,000 fatalities according to coronavirus. Is that right? He said, actually, no, the number's not that high. Interesting. And he talked about the fact that, well, while there may be some people who are falling victim to coronavirus, we also are not driving as much. The number of traffic accidents and other fatalities have dropped. Oh, okay. And then he says, there's another thing going on. If you look at the 260,000 people who have been recorded to die from coronavirus, something like 70 to 80% of them have pre-existing conditions. And on average, the 70 to 80% who have pre-existing conditions, they have an average on the forms that are filled out when someone passes away, they have an average of 2.6 other contributing factors. And of the excess fatalities, only 2/3 of those is coronavirus even one of the factors. So where are these other excess fatalities coming from? Well, one thing that we're seeing some interesting anomalies in is the number of fatalities from Alzheimer's has grown this year over last year, which is very personal to me because my mom has Alzheimer's and she's in a facility right now. So I say all this to say, here we are in the middle of an event, this pandemic that's having one of the largest impacts in modern history on all of human society. And there are questions as to whether or not we are looking at the right data. Well, let's go back and pretend that once again we are John D. Rockefeller, and we're trying to look at what's happening in the oil business. And you said, well, John, you control U.S. oil industry, the total amount of oil business that you impact in the 1970s is massive. You got the Middle East oil embargo. What should we look at to not just think about the next 2, 3, 4 years, but long term? What should we look at? We look at one other interesting piece of data beyond just price of oil and number of drilling rigs. Let's look at the production and consumption of oil around the world, say for the last 30 years. Now, I don't have this for 1950s and 40s and 30s because at the time we weren't tracking good data, but I can show you today what they could have looked at if they could have looked back just the last 30 years. From 1980 to 2015, these two lines, the red and green, and if you can't make them out individually, that's okay. What you'll notice that these are production and consumption of oil globally. And you'll notice that they hug together. They are off by 1, maybe 2% at any one time in history. Now, if I were to show you 2020, what you'd see is production and consumption were off by nearly 30% at one point. Just like when the Middle East oil embargo hit in the 1970s, and an artificial injection of market influences happened, the same thing happened with coronavirus. But it didn't change the overall data, which is, in general, you'll look at the trend of oil consumption. At the end, the United States in the 1970s ramped up its oil production by nearly double. Yet the world was not demanding any more oil. It was just having to come from different places. In fact, if we were really thinking, we said, wait a minute, in reaction to all of this Middle East oil embargo and oil shortage, the US Congress passed the CAFE standards, or the requirements for fuel efficiency of vehicles to go up. And the Department of Transportation by the 1970s was forcing cars to get more car efficient. We would have said, wait a minute, the oil demand is not going to grow near as fast, and we just put a whole lot more oil on the market. We need to be prepared for the fact that these two lines are going to be way out of whack. What can we do about it? Now, you may say, yeah, but Ryan, that was all the way back in the 1970s. I mean, let's talk about some things today. I mean, what kind of things might we see today that we could look at and say, maybe we can see something that somebody else doesn't see? Well, let's look at some corporate financials, all right? Let's take a company, all right? One company that produces something. I won't tell you what it is right now, but let me give you some numbers just to put it all in perspective. This is company one, produces 10.8 million units. All right, this is a company producing a product, and they produce 10.8 million of that product every year. This company has a revenue of $283 billion, and their earnings, their corporate profits last year were $20 billion. Okay? You with me? Now let's compare that to another company. Oh, by the way, this company's market capitalization, this company is worth today $87 billion. All right? Let's compare it to another company. A company in a similar market, a competing company, produces 500,000 of these units. Company one produces 10.8 million. Company two produces 500,000 of these units. This company's revenue is $25 billion. This company's earnings are $416 million. So by comparison again, company one, $283 billion in revenue, $20 billion in profit, and $87 billion in market cap. Company two, $25 billion in revenue, less than 10%, $416 million in profit. This company's market cap today, $580 billion. Compared side by side, you'll see literally 20 times the productivity. You'll see more than 10 times the revenue. You'll see 40 times the profit. And yet this company has a market capitalization of $580 billion. It is the eighth most valuable company on earth. Some of you by now have figured out who this is. Company one is Volkswagen and company two is Tesla. Now, why do I pick on this example? I will tell you that in order for Tesla to validate this market capitalization based on traditional price to earning ratios in the automotive industry, which tends to run around PE ratios of around 20, Tesla will have to produce more cars than Volkswagen, Toyota, Honda, General Motors, Ford, and Chrysler combined. They will have to produce more than 60% or 70% of the world's cars. So you look at this and say, man, I don't know if Tesla is a great investment. Great cars, great product. Not sure that the data backs up what a lot of people are buying into. Ryan, some may say, yeah, it's just a one-off. After all, Tesla is the most shorted company in history. Well, let me give you another example. Is that just a one-off? No, let's look at two other companies. Here's a company that produces energy. Company one produces 38 trillion BTUs of energy per day. Company two produces 3.8 trillion BTUs, 1/10. Company one has $266 billion in revenue. Company two, $17.5 billion in revenue. Earnings of company one, $14.3 billion. This is last year. Company two, $3.4 billion. And if you take out government subsidies, $400 million. Market cap of company one, 160 billion. Market cap, company two, 145 billion. In other words, these companies have roughly the same value, even though this one produces 10 times as much energy and has somewhere, depending on government subsidies, between 30 times and 5 times the profit. Company one is ExxonMobil. Company two is NextEra Energy. Why then are people investing in, why have they pumped the value up of Tesla and NextEra relative to Volkswagen and ExxonMobil? Because it's sexy. People are envisioning that the world is going away from hydrocarbons and away from oil and gas. And it's true, there is a transition happening. And they're betting on companies like NextEra, who about 2/3 of their portfolio comes from things like wind and solar. They also have nuclear and natural gas, but because of their footprint in alternative sources of energy, their valuations are skyrocketing. Now, what would we do with all of this data? After all, Ryan, that's interesting insight. But how do we predict the future? What you're talking about with oil and with coronavirus and with baseball is trying to look out and predict what's going to happen. Well, let's come back to energy. After all, one of the things that is crucial about energy, we tend to think of energy in terms of stock markets and energy prices and BTUs. In the end, energy makes the world go round. If you look back over the last 100 years, the growth in modern society has been fueled, quite literally, by access to affordable, reliable energy. And when it comes to predicting the future, we don't have to get that creative. This is a graph of the global demand for energy over the last 40 years, and you'll notice that it goes up virtually every year. There are a few anomalies where in given years we had the big recession in 2009. I'm sure when we look at the end of 2020 data, it will be a little bit of a blip. But whereas economies will fluctuate in markets and oil prices and corporate profits, you'll notice that the trend in energy is up. In fact, this is so predictable that the EIA, the Energy Information Agency of the United States, feels comfortable projecting out energy demand for another 20, even 30 years. You'll see here projecting out all the way to 2050. Where big growth in energy is going to come from. And it's not going to come from the Americas. It's going to come mostly from Asia and developing new economies, new urbanization. Some will say, well, yeah, but Ryan, a lot of that energy is going to come from alternative sources, right? I mean, after all of this growth in Asia, I mean, we're going to see a lot of that come from wind and solar. A lot of it will. However, let's look at where the trends are in terms of prices today. You can see where the cost of solar on a per kilowatt hour, per kilowatt basis has dropped dramatically in the last 5 years. You'll see that wind has dropped a little bit, even though it was already down low, but still, relative to natural gas, there are healthy margins higher. And in countries that don't have unlimited wealth to put into alternative energy sources, there are big questions about, will they invest here or will they want to invest here at half the cost? This disparity in prices is still causing us to project out that, yes, while renewables are going to grow at a faster pace than all other energy sources, you can look at in 2050, the EIA is estimating that still the net amount of energy coming from traditional sources is still going to increase, just not near as fast as renewables. So as we look out in the landscape and say, well, okay, what do we do with all this? We're going to talk about how to compete, knowing things or interpreting things that other people aren't looking at. And this is where the topic of complex systems really takes shape. I mean, just in my 30 minutes I've spent with you so far, I've talked about just in energy. We've talked about energy production. I've talked about global demand. I've talked about global supply. I've talked about cost of energy sources. I've talked about regional geopolitical events. We've talked about things like pandemics causing massive destruction in demand. We've talked about investments into alternative energy sources. We talked about government subsidies when I pointed at NextEra Energy. So what does this mean in terms of our ability to analyze systems? If you go back and you Google the Corsair, I don't mean modern products, I mean the World War II plane. You'll see a plane that was built by Vought Aeronautics. And this was the plane, if you look at the front of the plane, that had the wings that went down first and out like this. That wing design was conceptualized by a group of 3 engineers, one of whom was a guy named Al Sabilla, who was my grandfather. One of my most prized possessions is a group of books, because in my grandfather's massive family, I was the only engineer. And so when my grandmother passed away, she gave me his books. I've got a book that was copyright 1919, and it's his old materials book. The fascinating thing is when I graduated from Texas A&M in 1998, my materials book and Al Sabilla's materials book didn't have a lot of new information. There's not a lot of differences between them. However, as engineers today, we are being called to do something differently than engineers have done in the past. And it's to consider extremely complex systems in ways we've never done before. How do we take all of these different variables and all of these different inputs and analyze them in ways that we can make better decisions? Well, to that, I'm going to use one last example here. This is a flow chart of a small refining unit, of a piece of a refinery. Now, this graphic is not intended to be instructional on its own. It's the concept. Imagine if you were working in a refinery today, or a wastewater treatment plant, or a mining operation, or a chemical plant, and you were challenged to be competitive in a world where you know the world wants more energy, wants more product, but because of coronavirus, because of sensationalism in politics, because of economic trends, because of what's happening in other nations who are funding their refining infrastructure, you know that things are incredibly challenging. How do we model out these complex systems in ways we've never done before? Think about the numbers of inputs that we have in this system. In this graphic here, I'm showing around 300 different assets. These are pressure vessels, pipes, separators. There are exchangers, there are pumps, there are compressors, and heaters. All of these are required to make this system run. And in all of these assets, there is thicknesses and temperatures and pressures. There's weld design information. There's process stream information. There is heat or fire rates, and there are a myriad of different data points coming in every day that tell me something about this system. And if you look 5, 10, 15 years ago, we didn't have the ability to do all of this analysis real time. In fact, what a lot of engineers like me did when we came into the industry in the late 90s and 2000s, we learned how to take one pressure vessel and look at it in detail and figure out what was happening and analyze all the nuances. And that is still going on in large part for engineers today. But what engineers are going to be more and more called to do is look past the individual things, the rules and the best practices, the codes and the standards, because we'll have computers to do that rapidly. Instead, how do we create models of very complex systems and now model all of these various inputs real time? The ability of engineers and scientists and data professionals to do this work will be the difference between the companies who thrive and the companies who die. It's going to be the difference between societies and economies that grow and those that shrink. It may even be the difference for those pieces of our communities that are so heavily hit by a pandemic and those that are able to survive and deal with it in a way that's not quite as painful. So my challenge to those of you listening to my guest lecture today is this. As you think about the shift in the world and the traditional ways that we have been successful in engineering for decades, think about the fact that the ability of machines, of computers today to do a lot of what we have done is getting faster and faster. What we have to do now is to combine these traditional engineering techniques, materials and thermodynamics and mass transfer, heat transfer, combine those with data systems and data analytics in ways we've never done before. While this may sound, sure, Ryan, we've done this with process simulators before, absolutely. But getting even more detailed, more real-time, integrating data analytics into our decision-making today, that is the future of engineering, that is the future of industry, and that will be the future of energy as we know it. And with all of those ideas laid on you, I want to hear from you. I know I've thrown a lot of things at you today. What things struck you? What things do you challenge? What things do you think I'm thinking about in ways that you don't understand? I want to hear the questions from you. I'd like to, and I'll answer whatever questions you have for me. think I saw one come up in the chat. Oh, here we go. Ryan, my question is about how much of a role will grid scale energy storage, example, pump storage, hydroelectric, and compressed air energy storage, play in energy markets in 10 years, in 20 years? What do you say, Trevor? How are you? Okay, so the question is, what role is energy storage going to play? In fact, it's a great one, Trevor. I'll reference my drawing up here. Energy storage is going to be one of the single biggest pieces of energy transitions. In fact, if you imagine this is a complex system, but instead of having 300 assets like I've got here, imagine it is a system of, say, 500,000 different assets. And the beginning of the system is, say, a well or a turbine or a photoelectric cell. And the end of the system is a consumer using energy for transportation, home, HVAC, conditioning, whatever. And the ability to intermittently store that energy is going to be huge. And we've seen that costs of that and the reliability of that is a big issue. In fact, just this last year, we saw an issue again in California as they struggled with their grid reliability, and they are making substantial investments in storage to try to provide reliability. And let me in fact weigh in with a very simple anecdote here. One thing that is true, and people debate, climate change and how we transition. Look, the fact is this stuff is coming. It's just a fact, and the United States arguably will be one of the leaders in the transition, not because of political pressure, as much as it is we don't have the oil reserves of other countries around the world, and we also have private companies who are maybe currently making a lot of traditional energy, who can now invest those profits, invest that capital to stay a relevant energy company, and yet move into a less traditional form, things like hydrogen and solar and others. So let's go back to this though. One thing that is true of the American consumer, and this is polling data, when it comes to energy, American consumers they have three priorities when it comes to energy, and they are in this order for about 92% of the population. Energy has to be reliable, then affordable, then they are willing to lobby, or they want it to be green or whatever other descriptor you want to put on it. So one of the challenges with storage is how expensive can it be to enable the system to be reliable and still be affordable so that the end consumer is willing to pay for it. And that is a challenge that economists are analyzing constantly. And so, Trevor, back to your question, the ability to have affordable energy storage will play a massive role in the transition, whatever it is, and how quickly it happens. All right, what else do we have? So, Stratus, do you just want me to answer the questions on the chat, or do you want to?
No, I have been muted, so now I'm afraid to speak, Ryan, okay. Before we go ahead, just want to say a few, remarks on your presentation. First of all, to thank you for a very inspiring and very, enthusiastic presentation that covered a lot of issues, and we made us think about the energy future and the transition and all the use of data analytics and the richness of information and decision-making that we can get out of them. There are a wealth of questions, and in the chat and the question and answers that we are not going, we're going to take them in some order. And I would like to start by one of them is talking about what is the biggest challenge in moving, this comes from Ellen Basquaret, what is the biggest challenge moving from data collection to action?
From data collection to what?
Actual implementation, yeah.
Yeah, it's a great question. And in fact, I will tell you this, there is a very common, if you're in any of the traditional industries, manufacturing, energy, even some of healthcare, there is enough data available. There's actually, I would say, way too many companies and way too many people are trying to invest in new data, as opposed to your point, investing in what we do with it. I would say the single biggest challenge is this. The data analytics models we have used for retail, things like Amazon, do not work in complex systems. And let me explain why that is. If you look at Amazon, literally something like 10 million people an hour go on Amazon. So the amount of data that we are, am I locked up? Can they? No, it's just us? Okay. The amount of data that they are collecting is sufficient to find massive amounts of patterns in. So for example, when I go on to Amazon, it knows I'm a Caucasian male, 45 years old. Here's the last things I bought, and here's what all the other people like me and my wealth bracket are looking for on Amazon. So it shows me those products. Now, compare that to say refineries. There's only 130 refineries in the United States, 600 of them around the world, and they are all unique. So because of the models that we use in a lot of the software and retail spaces are based on large amounts of correlation. But correlation doesn't work when you don't have enough sample size to get good data. Therefore, we need better algorithms. So you asked the question, what's the challenge, or what's the opportunity to leap from all of this data to action? It is to, and this is where human beings and experts can be extremely useful, is to design more sophisticated algorithms to interpret smaller data sample sizes to give us real insights. Think about it this way. If I were to ask an expert to come in and opine on something, say brought an expert into a mining operation, and I said, I've got this operation going on. I want you to come in and help me figure out how to do things more reliably or more productively. They're going to look at a bunch of information, and they're going to make some conjecture, and they're going to try to make some judgment calls. Well, is it possible to take some of the logic that they're using in their head to build algorithms that would make the decision more quantitative? In doing that, we do two things. One, we make that analysis happen faster. And two, at the end of it, we can check the accuracy of our models to see if empirically we got the results we were expecting. By doing that, we can constantly improve our algorithms to get much better results from all that analytics. And that's probably the biggest single gap, the biggest single area that is in demand in the world of data science and the world of engineering today, is building those algorithms that take the data we do have and produce better results. Stratus, can you still hear me?
Mute me? Okay, now I'm muted. I'm muted from the system. Now I'm unmuted. Yes, we can hear you. Very good. I would like to put two questions together for you. One comes from Professor Eduardo Gilding, who says, as a professor of petroleum engineering, what do I say to my students? Do they have a future ahead of them? Thanks for the presentation. The other comes from Augusto Moraes. Do you think we are anywhere near a change in mindset and public opinion regarding nuclear? If not, what would have been to happen before it becomes acceptable to the public and so forth? And at Texas A&M, we have great departments, both the petroleum engineering, perhaps one of the two top of the country, as well as an excellent program on nuclear. So your thoughts on this, especially as you navigate the energy transition?
Sure. And look, I'm a mechanical engineer from A&M, as Stratus said, and I'm heavily invested in the energy industry, mostly in both in terms of our company, Pinnacle. We do most of our work in oil and gas. And I'll reference this graph. You tell your students right now, they're going, oh my gosh, there's no future in oil and gas. That's not true. I think that while the biggest growth area for energy from a percentage basis is renewables, there's no question. You'll look and see that the oil curve here, the natural gas, petroleum, other liquids, they still are both on growth trajectories. And I'll add some color to that. If you're a growing economy, you're transitioning from a third world country to a second world country. You're going from a predominantly predominantly rural agrarian society to more urban. The sophistication required in electric grids and infrastructure to run renewable energy is very difficult to achieve. Now, in a modern day society like the United States, we already have some of these sophisticated grids. It's not as big a challenge to overcome. Still requires tens of billions of dollars of investment, but it's more within our grasp. If you're, once again, a developing economy in, say, Africa or South America, very difficult. However, taking a gallon of gasoline and putting it in a car, that you can manage. So what you're going to see is, while, say, countries like the United States probably level off their oil consumption, I believe that other countries will more than make up for that in their growth in energy consumption. And a lot of that is going to come from hydrocarbons. And in fact, you'll hear some of them make public statements that, look, we get it. You know, you Americans really love it's really sexy to use, solar and wind and all that kind of stuff. But at the end of the day, you guys built your countries for the last 100 years using oil and natural gas. We are going to do the same thing. So yes, there is absolutely a future, but it is going to be a more competitive future. And we have to compete with the fact that I believe the Chinese right now are making strategic investments into their oil infrastructure with the design on let's make the profits and make the money for the next 20 or 30 years in oil and gas, and then let's funnel that money into alternative energy sources. So hopefully we don't artificially here in the United States push oil and gas out of the country and miss the opportunity to capitalize on that crucial energy supply for the next 30 years. So to answer your question, yes, there is. The question will be, how much of it are we able to do here at home? And you'll hear me and others lobby hard that we need to continue. Oh, nuclear was the other question, Stratus.
Yeah.
I can't opine on that as articulately as I'd like to, although I would say I think there is a growing sense of acceptance that nuclear can be done safely. And it's amazing how the Fukushima power plants can kind of raise the ire for a while, and then Germany shut some of its plants down. But people can become a little desensitized after time and say, look, we do this safely. So when you're talking about committing resources, especially government resources, I think that over the next 5 to 10 years, you're going to see more and more acceptance of that as an alternative energy source, especially with natural gas prices going up, which they are. I believe they're going to go up in the future. Electricity costs are going to come up, and nuclear becomes a lot more economically favorable, which will help as well.
Now I'm unmuted again. All right, very good. There is another sort of theme around questions around hydrogen, and then about also, if you wish, like waste products in the energy sector, like part of, let's say, sustainable and circular economy type of concepts, life cycle. So can you give us your remarks and thoughts, and from your experience, what do you think this, as we manage the energy transition of the future, what is the role of thinking ahead in terms of circular economy, life cycle analysis, waste to products, to energy, and all these kinds of concepts which might be prevailing in the near future?
Yeah, I would say this. I don't think they're going to be prevailing in the near future. And look, there is a lot of public debate about this right now, and coronavirus has really thrown some artificial indicators in there. For example, just earlier this year, BP came out and said that one of their models shows that oil demand around the world peaked last year. I don't think that's true. I think that the global demand for energy is going up. There's not enough energy, not enough ability, not enough infrastructure to get that energy out of non-traditional sources like solar and wind and hydrogen and those sort of things. So when we're talking about energy transition, logically speaking, you're talking about a 20, 30, 40-year process. So let's just lay that out. That's the timeline that I think this is going to happen. In fact, I do not think we will see a time in my life where most cars on the road around the world will be electric and not hydrocarbon based. That's my theory. Now we may get to a point where it's close, but it won't be, you won't see, I don't think in my lifetime you'll see 70% of cars be electric or anything like that. So now let's talk about some of the other ones. And the big challenge for this, Trevor asked about storage. Storage is one piece of the large scale infrastructure challenge. Now, when you talk about infrastructure, we're not just talking about pipelines and power lines and storage facilities. We're talking about mechanics. Who fixes the car? That is not, right now, if your car breaks, you can run down the corner and there's a couple different service stations who can work on your car. Well, if we are all shifting to new designs of cars, it takes time for us to have the infrastructure to support that. If you look at If you look at things like, okay, let's say people talk about hydrogen. I mean, hydrogen has some really interesting potential. However, the infrastructure required to produce hydrogen, store it, then use it in cars safely, and that all takes a lot of time, not just for the infrastructure to support it, but then also for people to get comfortable with it, knowing how to use it. So while it's probably coming faster than we thought it would have 5 or 10 years ago, I think it remains to be seen how quickly it will come to bear. If someone asks, I saw somebody asked a question, kind of what should we be telling students today? Simply put, I would be telling students today, there is absolutely a future in energy. There is no question about that. And what students can be doing today is say, you shouldn't, if you're graduating today and you say, well, I'm just going to be an oil guy or girl, then you're probably missing an opportunity. I can tell you as a man who runs a company of nearly 700 people, most of our customers are oil and gas, but that's not all we serve. We serve mining, we serve the wastewater industry, chemicals, and we are leaning heavily into other areas. Eventually, what about wind turbines? They need reliability programs as well. And there's some theory that wind may be, the people are getting less and less comfortable with the amount of footprint that windmills take up. And so what does that mean? So what I would tell you is the evolution of energy sources is going to continue. Oil, natural gas will play a massive role, but so will others. So what students can be doing is saying, look, when I go in the energy industry, they should be thinking energy, not oil and gas. And as they will see opportunities in other areas, every single one of those spaces I just talked about uses pressure vessels and pipes. They all use control systems. They all use data to model out their operation. They all have opportunities to make systematic improvements. And so regardless of whether you major in petroleum, aerospace, mechanical, chemical, biological, biomedical, there's opportunities to do that analysis to produce better results, regardless of when or how the transition comes.
Very good. I mean, that reemphasizes the importance of our Texas A&M a master program in energy, which exactly directs students to think about the global aspects of energy and not specific areas, and creating this panoramic view. Thank you for reinforcing this message. There is a question regarding the data analytics and machine learning techniques that you highlighted, especially with what is from Mr. Stefanos Baratsas with regards to the incorporation of experts' knowledge. So how do you see for instance, because we have lots of fundamental models, we have experts, we have data, we have techniques. How do you see those synchronized and dancing together?
Give me just a second, Stratus. I'm going to pull up my whiteboard here. Okay. All right, can you see my whiteboard?
Yes.
Okay. All right. What I'm going to do here is explore something with you that is, it's a flow chart in which we're going to think about a decision process that is not based on a human being's activities, but based on the flow of data. And this will help articulate the integral role of experts in data. So imagine here, I'm going to collect some data, okay? And I'm going to collect some data, and that data I'm going to use to do some work on, and how I'm going to, with that data, the first thing I'm going to do is I'm going to organize it. Okay. Now, a lot of times we don't think of this as an engineering step, but it is, and let me explain why. There are 3 things I have to do when I look at data. I'm going to say, what if this data is real data? In other words, I've got it, it's useful, I know I can use it in the way I want to use it. Where can I make assumptions to help fill in the gaps? And just where are there gaps? Where do I not have the data I need? So if I know that here's the pool of information that would help make a good decision, I can gather what I've got. Then I need to figure out what's real, what can I fill with assumptions, and what gaps do I have. Now, from there, I go and I say, okay, well, I've got another step, which is analyzing that data. Now, similarly, I've got 3 steps here. I've got algorithms, Algorithms where I apply either an empirical formula or a Newtonian formula, something that takes that data and takes it based on data I have, gives me another bit of insight. I've got expert input, expert opinion. In other words, my specific area of expertise was risk analysis for a lot of years. So I can say, all right, given a bunch of information, I can formulate an opinion based on that data. And then once again, I've got gaps. I've got a bunch of data. I know it's good data. I'm not sure how to analyze it, who to get to do the work to get opinions on the other side. And then out of this, I get some sort of action or a plan. In other words, the data forms the decision as opposed to the person making the decision. A way to look at this would say, if I say before, I am not going to invest in this stock unless I'm convinced that the risks of a downside loss are 10% and the probability of upside gain are 30%. Well, then the decision was already made. I already laid out the criteria. I now use the data to make the decision. And the data goes from all the history on that stock. What data do I have about the future performance, the market that it's in, everything else? Where can I make assumptions based on what I see happening in other areas? And then what do I not know about that stock? What data do I not have insight on? Then over here, I say, well, I've got some algorithms to do some projections. I could call them, stock brokers or stock analysts, market analysts who might know. Then there's some ability I don't have. But in the end, I come out with some projection for potential upside, some potential for potential downside, and that forces me to take an action based on that decision. So when someone says, well, Ryan, so what you're telling me is the experts really get involved in helping to define what assumptions might fill in for gaps in my data, and my experts can help draw opinions where I don't have good algorithms to form them. Now, at the end of the day, what good systems engineers should be doing is trying to minimize these. We should be trying to maximize these things. We want to maximize the amount of real data we have, and we want to maximize the amount of algorithms that we're using to make our outputs more and more quantitative. But you can see in very complex systems where I'm not dealing with, a dozen or 100 or a couple hundred data points, I'm literally dealing with 1 million data points a day. The only way to do this is with real data and algorithms, because there's no way an expert can give me opinions and can give me assumptions on a real-time basis to do the system analysis. So back to answering the question here, if I understand this data flow from original data gathering to action, then I know I can plug my experts into certain positions to make that process work.
All right, sorry. I'm not controlling my, the system controls the mute and mute. So we have like we have a complex system here. So, reliability is critical, as you highlighted. I think this is a great point that we stop the discussion. There are millions of other questions, Ryan, but I would like to take this opportunity on behalf, first of all, of the Texas A&M ecosystem, and on behalf of the Texas A&M Energy Institute, on behalf of all the participants, to thank you for a very inspiring presentation, which really gave us the opportunity, first of all, to think and reflect on the importance of the complex systems and the bright future that data analytics and quantitative analysis can bring into this. Thank you very much.
Thank you, Stratis. Is it okay if I end with one final goodbye? And I'm gonna give a plug here, if that's okay. A lot of people have asked me, Ryan, where can we get more information on all this? And that's usually the message I get. Just 2 weeks ago, I released a new book called Crucial Decisions, in which I explore a ton of this. And so if you're interested and you go and you get the book, it's on Amazon, let me know. I'd be happy to sign it for you or to interact with you on it. I'd love to get feedback on it. So we've gotten a lot of good reviews, but I explore most of what I talked about today in that book and would love to get feedback.
Excellent.
Thanks for having me, Stratis.
Thank you. Very good. Bye-bye. Thank you.